But nowadays, computers can write anything from news articles, emails, and poetry, and even generate code in Python or JavaScript. And Google search doesn't just return links, it actually answers your questions, and it can translate foreign languages for you. And of course, there's personal assistants like Siri and Alexa. They've been carrying out lots of simple tasks, and chatbots are helping out with many of the customer service jobs. All of these are some examples of computers interacting using natural language. That's our human language. So natural language processing is the field to get computers to understand and produce human languages, or NLP for short. And the people who work in NLP study a combination of linguistics and also computer science. When I first started out in computational linguistics, way back in the dark ages, we hand-coded all the syntax rules, which is grammar, and semantic relationships, or the meaning. It was interesting, but really tedious. And I took a long break from the field, gave it a chance to mature a bit. And boy, have things changed. So there's a lot of jargon and concepts in NLP. So my goal today is to give you a general idea of how things fit together. During the 1990s, statistical modeling with n-grams were used to create language models. So what exactly is the language model and why all the statistics, right? So fundamentally, a language model is just trying to predict what words belong in a given context. So this is a famous quote: "You shall know a word by the company it keeps." That's the idea behind the statistics, right? The grammar or the syntax of a language follows these very strict rules of word order. For any word in a sentence, if you just look at its immediate neighbors, you can usually tell it's part of speech. English adjectives are always followed by nouns or other adjectives, and prepositions are usually followed by noun phrases. And so there's a bunch of these rules, and even with words further away, they still give clues to the meaning or semantic relationships. So if you hear the word doctor, there's likely to be other words related to health or medicine. And in a sentence with teacher, you might expect words related to school or education. So humor me a bit. Think back to when you first learned English or whatever was your native language. As a child, you were immersed in language from just everyone talking around you. Long before you were ever explicitly taught the rules, you already had a strong intuition of what's right and what's just sounds wrong. You've internalized the statistical probabilities of what sequences are likely and what's not. And so that's your own internal language model. With statistical models, they're built on these n-grams, and the n just tells us the length of the sequence we're counting. For example, if we're looking at single words, we'll count unigrams. So let's pretend that we have Hamlet's to be or not to be speech as the corpus or our text data set. So the unigrams are to, that occurs twice, be, also twice, or once, not, also once. Then the two-word sequences are bigrams, and here we have to be or not, not to. And now we have three-word sequences called trigrams, and now we have to be or not to, not to be. And so we count all those and continue, right? And after that, there's 4 grams and 5 grams. So we can use all these counts and statistics in something like a hidden Markov model to do something meaningful. Okay, back to our timeline. In the 2000s, computers got more efficient. There's more and more big data out there. And neural networks, which actually had been around since the 50s, they were sort of rebranded as this new and exciting deep learning. And that revolutionized all kinds of industries, especially computer vision made huge leaps with AlexNet trained on this massive ImageNet data. But neural networks only understand numbers. And well, our human languages aren't usually numbers. So somehow our text input have to be converted into numbers. And one idea is to use our dictionary, which is full of all these vocabulary or token. And the tokens can be words or subwords or even characters or bytes. It all depends on how the model defines and builds its dictionary. So maybe we can use the input tokens index from its dictionary. So that's okay, but the numbers don't really give us much information about the meaning of those words. Then in 2013, Google researchers created Word2Vec, which is just these high-dimensional word vectors. And we can kind of think of a vector as a list or an array of hundreds or thousands of numbers. Now, I don't know about you, but most of us mere mortals just aren't very good about thinking about these 100-dimensional space, right? But we're kind of stuck in our little 3D world. And to help us visualize these high-dimensional vectors, they're reduced or embedded into 3D space just for visualization purposes. And the word vectors are also called embeddings. So take a look at this. The basic idea is that each of those high dimensions in the embeddings represents something meaningful about the word, some kind of a feature. And the really neat thing is now, just look using vector arithmetic, Word2Vec could actually solve all these word analogies. Take capital cities. You can do Athens minus Greece plus Norway, and it'd come up with Oslo, or a man-woman relationship. Brother minus sister plus granddaughter would give you grandson. With opposites, impossibly minus possibly plus ethical equals unethical. And plurals, mice minus mouse plus dollar equals dollars. So just by looking at tons and tons of regular English sentences, Word2Vec managed to learn these syntactic and semantic relationships without anyone explicitly encoding them. So just think, no one had to hand code all of these cities, opposites, and plurals. I mean, this is pretty amazing. So a bit after Word2Vec, Stanford created another language model called GLOVE, short for global vectors, and it combined the probabilities from Word2Vec, but also included some ideas from the statistical N-gram models. And both Word2Vec and GLOVE were great for finding good representations for words. But then there were other neural nets like RNNs, GRUs, and LSTMs, and these focused more on processing sequences. So RNNs are recurrent neural networks, and you'll see them in diagrams with this little recurring loop. And that's just a shorthand for this unrolled version, which means that at each time step, a single input token is processed and the output is passed on to the next step of the sequence. Then rinse and repeat for each of the tokens. And if we zoom in, the processing inside of basic vanilla RNN is just applying a function. But later they came out with GRUs, or gated recurrent units, and LSTMs, long short-term memories, which added extra elements to help remember information from a little further back in the sequence. But fundamentally, all of these are variants of the original RNNs that process sequences one token at a time. So they can be a little bit slow. Then a huge breakthrough came around 2017, 2018 with transformer models. And the key idea was to use this attention mechanism that could look at the entire sequence all at once. So it didn't matter if the related tokens were far apart in the sequence. And since they no longer had to work with one token at a time, things could be processed in parallel. And suddenly we could train more data with bigger models much faster. And that led to the rise of these large language models. And when I say large, I mean like humongous, millions and billions of parameters trained over weeks or months. And the most famous of the transformers are probably GPT and BERT, but there's plenty of others. So next time we'll take a look at transformers, okay? See you later.